Looking up at the night sky, the stars and galaxies appear to be randomly arranged. But this is not true at all. Despite being random, the universe is not a random noise of objects. It is full of stars at our fingertips. But if you go beyond 100,000 years, you leave the Milky Way. Beyond that would be the galactic sea, 2 trillion galaxies in total. They can be found in our observable universe. They come in different types, shapes, sizes, and masses. However, in addition to galaxies, space also contains galaxies, star clusters, clusters of galaxies, and even superclusters. Certain objects in the observable universe have been identified by astronomers as large-scale structures because of their incredible size. The largest of these span hundreds or even billions of light-years. Because of their elongated shape, these objects are called galactic filaments. These filaments join each other and fill the empty space, as if forming a three-dimensional web. But this is not so. Voids and galactic filaments can form large walls. But what do they represent? The walls of the universe are generally thought to be the flat structure of galaxies and voids, the third largest structure known in the universe. For example, the CFA2 Great Wall was discovered in 1989 based on the transformation of distant objects. It is the third largest mass observed in the universe. This object is a flat structure of filamentary clusters of galaxies, surrounded by voids. The voids are filled with dark matter, which defines the structure of the universe on the largest scales. This object is located about 200 million light-years from the Milky Way and is 500 million light-years long, 300 million wide, and 15 million light-years thick. However, the exact size of this object is still unknown, as clouds of dust and gas in the Milky Way obscure part of the Great Wall. Next, we visit the Great Sloan Wall. It's a complex of galaxy superscopes spanning 1 billion light-years. This is the flat structure of galaxies and voids. In length, the wall extends 1.37 billion light-years. It is located about 1.2 billion light-years from Earth. Thus, our galaxy, like its neighbors, is drawn into a certain space, and it is about 150 million light-years. Here's a surprise: we don't know exactly what's going on, although the name of this hidden anomaly is thought up, and it's easier said than done. Yes, we are talking about the Great Depression. Part of its mystery is because it lies in a part of the sky toward the center of our galaxy called the escape zone. There is so much gas and dust that it doesn't appear very far in the visible spectrum. The study of clusters in the escape zone served to solve the problem. X-rays were used to study regions that could easily overcome clouds of gas and dust. A galaxy cluster is a source of X-rays, making it easy to observe and study. In fact, the escape zone is now very well understood. Galactic gas and dust are also easily detected by radio waves and infrared light. Recent research has found less massive galaxy clusters than expected in the suspected location of the Big Dipper. Nevertheless, a gravitational anomaly near the center of the Big Dipper, the cluster Abell 3627, appeared with enough force to tear apart the spiral galaxy ESO 137001, or, as it is known, Medusa in the constellation of the Southern Triangle. Also, a closer look at the containment zone reveals a large supercluster of galaxies called the Noggle Cluster instead of the Big Dipper. Its mass is about 1,000 trillion solar masses. These are thousands of galaxies. Although the Noggle Cluster is large and local galaxies are attracted to it, the motion of local galaxies cannot be fully explained. And the mass of the Great Attractor is not enough for such an attraction. A study was conducted, and it was calculated that the contribution from the speed of the Great Group to the speed of the local group is 44%. Others are related to global currents, in which a significant area of the local universe, including the Great Attractor itself, is moving toward another object. Continuing their search, they discovered an even larger cluster of galaxies located more than 600 million light-years away from the Milky Way, the Great Milky Way. We are talking about the Sheppey supercluster. It has more than 8,000 galaxies and a mass of more than 10 million suns, making it 10 times larger than the Noggle cluster in the Greater Tartu region. The Sheppey supercluster is the most massive supercluster of the 220 known supercluster galaxies in the observable universe. Most likely, once it reaches the Great Gravitational Region, the Milky Way will transition to a more massive object as part of the entire local group, namely the Sheppey supercollapse. The usual logical questions arise. What will happen to the Earth? What's in it for humanity? But rest assured, everything else needs to be taken care of. No one knows what this means or whether our planets are in danger. Astronomers say it will take years, perhaps decades, for them to learn more about this anomaly. Some experts do not consider this dangerous. Others believe that all galaxies and clusters will merge into larger and larger cluster regions, and thus the universe will come to its logical end, a great contraction, theoretically expanding after the Big Bang. But there is no need to be angry. While the Great Depression or the Sheppey supercluster are not dangerous, we do face problems like climate change, the possibility of a giant asteroid hitting Earth or a supervolcano eruption causing a volcanic winter, an alien, or a crazed madman. Red button. There are many possible scenarios, but that's not what we're talking about today. As a result, we can note that the Big Dipper is a gravitational anomaly located in intergalactic space. In fact, it is a collection of many galaxies that have formed and are hidden, and more mass results in more attraction to other objects, including you and me. What do you think of the Great Attractor? What are your hopes that we will discover something new in this region of space where our little planet is moving so fast? Starry sky. It is what makes us think about the infinite space and our place in it. If we look at the night sky, we see many stars. You cannot count them. There are many of them. They all seem to be located very close to each other. But this is not so. There is a gap between them. The stars are medium. For example, the closest star to our Sun, Proxima Centauri, is only 4 light-years away. Sirius, the brightest star in the Northern Hemisphere's night sky, is 8.5 light-years away. These distances are huge, aren't they? However, there are places in the universe where there is nothing, and these spatial formations are called voids, which means void. It's hard to believe, but we live in one of these voids, and the largest known to science. But first things first. As we know, matter is not distributed evenly in the universe, but in the form of a giant web. Clouds consist of superclusters and clusters of galaxies, which in turn consist of stars, gas, dust, and planets. But voids are large regions between galactic filaments where galaxies and clusters are almost completely absent. Their average size can be from 10 to 150 megaparsecs. You understand that 1 parsec is equal to 3.26 light-years, which in turn is 200,000 astronomical units. How many light-years is a relatively small amount of 10 megaparsecs, 32,615,000 light-years? Now let's try to translate into kilometers. After such numbers, it seems that your work office is not far away and you can start walking safely, or to know the darkness. But it is not. A bit of history. Cosmic voids became a topic of astrophysics in the mid-1970s, after astronomical studies measuring redshift became popular and allowed 2 independent groups of astrophysicists to identify superclusters and galaxies in a wide distribution of galaxies in 1978. New research has added depth to 2-dimensional maps of cosmic structures, allowing the first 3-dimensional maps of the observable universe to begin. In these studies, the distances of galaxies were calculated from the magnitudes of their redshifts due to the expansion of the universe. With the advent of powerful enough telescopes and highly sensitive spectrometers, both on the ground and in space, the universe appeared to astronomers in which most of the work was concentrated in galaxy clusters, and a large part of space consisted of regions. Dense. Substance is 15 to 50% below average. A little later, astronomers from all over the world came to Tallinn, exchanged dimensions of galaxy groups and their distribution in space. After this historical event, the concept of the large-scale structure of the universe took on modern meaning. Jan Einasto, one of the pioneers of large-scale structural studies, recalls how astronomy journals rejected his paper describing galactic filaments and the space between them with the word K. Now look at the computer-modeled picture of the millennium. The process of formation of structures in a cube of 2 billion light-years is modeled. The first launch in 2005 used data from NASA's WMAP mission to study relic radiation from the Big Bang. After 2009, the Max Planck Space Observatory cleared the relic radiation parameters, restarted the simulation several times. Each time, the Planck Society supercomputer ran for a month. Finally, the simulation showed the formation of galaxies, their distribution, the appearance of galaxy clusters and the voids between them. Only the fission of dark matter, which begins much earlier than the first galaxies, can lead to the Avoida supergroup. In 2013, a team of astronomers concluded that the Milky Way and its closest galaxies were the bulk of the Laniakea supercluster of galaxies, including the Virgo supercluster, which included the Milky Way. A galaxy is a component of our solar system, and this whole structure is really gigantic, in the middle of the biggest void in the universe. The CBC is named after astronomers Ryan Yang, Amy Barger, and Lennox Cowie. It appears to be roughly spherical in shape, about 2 billion light-years or 600 megaparsecs in diameter, with the Milky Way several hundred million light-years from its center. It is the largest observatory known to science, larger than the Eridanus supervoid, and there is even a large supervid called APLP 36, about 400 megaparsecs. For comparison, our Milky Way galaxy is 0.3 megaparsecs, but these seemingly desolate intergalactic spaces are not as empty as astronomers thought. Further observation showed that there are other components in the space they occupy. The most common of these are protogalactic clouds. These are large clouds of dust and gas from which galaxies form, but this is not so. Light from distant galaxies and stars passing through the voids appear distorted. Researchers have long been unable to understand why this phenomenon occurs. It is known that light rays can be slightly distorted by the movement of the Earth's atmosphere, cosmic dust or defects in telescope lenses. But how to explain such a big break? To this day, it remains a mystery, and the hypothesized answer to this is the dark matter that is part of the voids. In theoretical physics, dark matter is a form of matter that does not participate in electromagnetic interactions and therefore cannot be directly observed. It is on the order of a quarter of the mass of the universe's energy and manifests itself only under the influence of gravity. Since there is no electromagnetic field, it is not an easy task to observe and study even with modern methods. However, using direct theories, special mathematical calculations and observations, astronomers show that such matter may indeed exist. In 1987, Tully and Richard Fisher discovered that our Milky Way galaxy is at the edge of the Great Void. They called the local gap. Scientists have embraced the idea of a local void, but the structure is still poorly understood because it is near the center of our galaxy, and therefore difficult to monitor. And yet, thanks to these results, the mysteries surrounding the expansion of the universe have been solved. Based on observations of the galaxy's motion, researchers have determined the mass distribution that explains this motion and constructed three-dimensional maps of the local void. The motion of galaxies is caused not only by the expansion of the universe, but also by the gravitational influence of neighboring galaxies and regions of high mass. As a result, galaxies appear to move away from denser regions and less dense void zones. In their new work, Tully and his team measured the motion parameters of 18,000 galaxies and created a cosmographic map that clearly shows the boundaries between the regions of matter density and the local halo. The same method helped us identify the boundaries of a supercluster of galaxies called Laniakea. Space is really like a giant sponge. Maybe someone's columns have been wiped. Long glowing filaments of millions of galaxies pass by, and star clusters are replaced by much smaller black holes. It is true that no one can see the universe. No matter which part of the mushroom the observer is in, the distribution of stars and galaxies will resemble the interior surface of the sphere where the observer is standing. The universe, as always, is full of mysteries, riddles, and unsolved problems. Man raised his veil to explore the voids of space. There are also upcoming discoveries that we will tell you about. And here, finally, we come to what is gradually called post-creation. Coined by British astronomer and author Marcus Chon, the term refers to what an observer sees outside the universe. And what he saw was a huge explosion. It is beyond the cosmic horizon. The fact is that for the first few 100,000 years, the universe was filled with furious plasma so dense and hot that light could not penetrate it. But when the universe reached 380,000 years old, the density and temperature decreased enough for electrically neutral atoms to form. At that time, the entire universe was as hot and blindingly bright as the surface of the sun. Therefore, if we look beyond the cosmic horizon, we should see the Big Bang no matter where we look. We can see that. That's right, this primary radiation has been going on for 13.8 billion years. Minus 380,000 years can be ignored. In addition, radiation was circulating in a continuously expanding universe. As a result, its wavelength was extended by about 1,000 times, and the glow turned into an unrecognizable hiss of radio frequencies. This whistle is commonly known as cosmic microwave background radiation or relic radiation. Advertising is the oldest signal that astronomers have been able to observe. We cannot come close to the birth of the universe. It is difficult for some people to understand that you can study continuously for decades. But truth be told, even dinosaurs with gadgets could have watched it. Of course, this begs the question, wasn't the birth of the universe a brief event? Shouldn't radiation from that era still be whistling? So how should we proceed? The explanation is also related to the subtlety of the speed of light. Let's do another experiment. Imagine you are in a large city square with thousands of people. Everyone is asked to synchronize their watches with each other and shout the word "caramba" at noon. But one detail. On a planet with an urban area, the speed of sound is only 1 meter per second, not our usual 330 meters per second. What happens at noon? You scream the word "caramba" at the top of your lungs. You can do it. The sound you make travels everywhere. A second later, you couldn't hear yourself scream. But at 12 o'clock, in 1 second, you hear the friendly banter of people a meter away from you. It takes a second for the sound to reach you. At 2 seconds past 12 o'clock, you can hear the word "caramba," but from people 2 meters away. Even a minute after noon, the scream reaches your ears. It comes from people 40, 70, 100 meters away. But the strange thing is, no one screams. Everyone on the field let out a short scream at noon, but you hear this nonsense called "caramba." If the area is really big, you will hear "caramba" for a long time, and you will not forget it for the rest of your days. This example helps us understand the following. A city square is a universe, a disaster of universal proportions, relic radiation shortly after the Big Bang, 13 falling relic radiation, 8 billion years ago at the point in our space where you are now, has long since spread out into the universe, but we still receive distant signals in space. These are echoes that resonate beyond outer space. Cosmology is an actively developing field of science, full of mysteries and surprising discoveries. We will never understand how it all began. But perhaps recording the fundamental gravitational waves created at the moment of the Big Bang will give us a new perspective on the birth of the universe. And space is curved. The radius is proportional to the value of the magnitude. And beyond the horizon, average things are just like us. The same microwave radiation, the same stars and galaxies, but in a different structure. The following example will help us understand. Imagine a universe where you can point a spaceship in one direction and return to where you left off. If our universe were a donut, such a flight would be possible, and we would know the size of the entire universe. The donut example is here for a reason. The fact is that relic radiation maps produced by telescopes such as WMAP and Planck have shown an interesting amount of missing perturbations on large scales. This interesting term refers to the deviation of a celestial body from its orbit due to forces other than the gravitational pull of the system's center of mass. such as other celestial bodies or drag. To determine whether these missing perturbations could be due to a densely connected universe, a number of computer simulations were run to see what the relic radiation would be like if the universe were a giant three-dimensional donut with space bound to itself. In all three dimensions. Yes, the properties of observed variability, that is, deviations from the mean value of a random variable characterizing a system of many chaotically interacting particles of rational radiation, indicate a lack of force on scales larger than the size of the universe. Missing perturbations mean that relic radiation fluctuations are absent on these scales, and our universe is multi-coupled and finite. To put it simply, there seems to be a lack of signals in the cosmic microwave background if the universe is truly infinite. One explanation for this is that the topology of the universe is curved back on itself like a donut or bagel on an intergalactic scale. Just as you can bend a piece of paper into a tube without changing its parallel properties, the universe can be like a donut if it stays flat. The researchers made the discovery by modeling the cosmic microwave background. Compared to the standard cosmological model, which is assumed to be infinite, we found a much better fit to the observed fluctuations. Such a universe must have boundaries, and the entire vast expanse may be 4 times larger than the boundaries of the human observable universe. It is 47 billion light-years across. The universe can be closed in 3 dimensions and actually has the shape of a 3-dimensional donut. Infinite universe models may scare some people, but you won't feel these limits, and you won't feel claustrophobia either. You basically live in an infinite universe despite its infinite size. But even if you don't reach this infinite alien universe, can you turn it around and get back to where you started? In theory, yes. In fact, light can travel infinitely throughout the universe. But it will take billions of years to get there. I have no idea what my donut-shaped universe looks like from the outside. Maybe lie down. Are we living in a vacuum big enough to solve the mystery of the universe's expansion? Before answering this question, it is important to consider that most theorists and astronomers believe that the universe is expanding. The so-called Hubble constant accurately determines the distance between space objects, but it does not always agree with observations. A new analysis of nearby supernovae suggests that this discrepancy may be part of our universe. It may be that we live in a very low-density space bubble that challenges our calculations, but according to the widely accepted Standard Model, this does not happen. It's been almost a century since scientists first heard about the expansion of the universe. The continuous expansion to the present day is the main evidence for the Big Bang. Since this ancient event, light has stretched to longer wavelengths, but studies of the cosmic microwave background allowed Edwin Hubble and subsequent astronomers to calculate the rate at which the universe is expanding. A commonly accepted value is 70 kilometers per second per megaparsec, or 3.26 million light-years. Thus, every million light-years, a galaxy or other object moves faster than 22 kilometers per second. In most cases, this constant is accurate, but various cosmic anomalies have led to disagreements in astronomy. The point is that when the expansion rate is measured using local galaxies and supernovae, this value is estimated to be about 10%. Recent observations have shown that the Milky Way is located in a vast void, where the density of matter is lower than that of the surrounding universe. This may explain why our universe is expanding faster, but there is one serious problem with this hypothesis. The Standard Model does not account for the low-density bridge in space. However, all this is based on Einstein's theory of gravity. But since then, we've learned a lot about the universe that most scientists didn't. The research explains the existence of space using Newtonian dynamics, or MUND, a theoretical model proposed in the 1980s as an alternative to dark matter. MUND has little variation in Newton's calculations of gravity, mostly in very fast accelerations. Using signals from nearby supernovae, the researchers confirmed that this change completely cancels out the conflicting readings, removing the Hubble objection. Of course, this is not a proven fact. This is one of several proposed solutions to the Hubble problem that other researchers should analyze. Another part of the scientific community suggests that this faster local expansion may be the same everywhere, or they cannot measure all the dimensions of the universe well enough to know whether the standard model is correct. The best way to find out exactly is to extend general relativity to scales larger than 1,000,000 light-years. However, there is currently no way to measure gravity without an object on the same scale. The assumption that relativity is not constant may lead to further controversy, as it did with Hubble. But let's return to the expansion rate of the universe. Usually, the rate of expansion is described by the Hubble constant, but different measurement methods give different results. In short, Hubble's constant determines how fast other galaxies are moving away from us, indicating the rate at which the universe is expanding. For example, using supernovae or analyzing relic radiation gives similar data: 264 and 244,000 kilometers per megaparsec. The new theory suggests that the universe is expanding about 3 billion light-years away from us. The standard cosmological model does not support this. Simply put, the researchers say that Earth could be in a relatively empty region. There is less foreign matter inside the cavity. This refers to the deviation in the value of the Hubble constant. Thus, according to observations and calculations, the universe is expanding 10% faster near our galaxy than it is far away. It is about 3 billion light-years from Earth. If the Hubble constant is true for the entire universe, then the universe must be younger. And this contradicts estimates of the age of the earliest stars and galaxies we have ever seen.